this video we are going to complete this table. So in this table we need to find the number of vertices, number of edges of these simple graph. Moreover, we need to identify whether they contain an Euler path, Euler circuit, Hamilton path or a Hamilton circuit. Beginning with the small recap of these terms, Euler path means we need to cover each and every edge of the graph exactly once, but the end points are different. And if the end points are same, then it is called as an Euler circuit. Hamilton path means we need to cover each and every vertex exactly once and the end points are different. While finding such a path, if the end points are same, then it is called as an Hamilton circuit. For more information on these terminologies, I have provided the links for your reference in the description. It is very easy to identify whether a graph has an Euler path or a Euler circuit with the help of two important theorems. So that is, if a graph has an Euler path, if and only if it has exactly two vertices of odd degree, and if a graph has an Euler circuit, if and only if the degree of each vertex is even. So let's explore these terms for the graph. So beginning with the complete graph Kn. So for the complete graph, total number of vertices are in a K1, it has one vertex. In K2, two vertices are there. K3, three vertices. So in Kn, so total number of vertices is equal to n. Now we need to find the number of edges. So for that, first we will count the degree of each graph. And after that, we will use the handshaking theorem, which says that total degree of a graph is equal to 2 times of number of edges. So in this case, so there are 5 vertices of 4 degrees. So it means its total degree is equal to 5 into 4. So now use the handshaking theorem. This is equal to twice of number of edges. So this implies E is equal to 5 into 4 by 2. Now for the K4, so degree of each vertex is 3. So there are 4 vertices of degree 3. So total degree is 4 into 3. That is equal to the twice of number of edges by using a handshaking theorem. So this implies the number of edges is equal to 4 into 3 by 2. Now let's try to generalize this formula. If there are n vertices, then the degree of each vertex is n minus 1. So in this case, total degree is n into n minus 1. Now if you divide by 2, you will get the count of edges in this graph. We need to identify whether this graph possesses Euler path or Euler circuit. So we know that for the Euler path, exactly 2 vertices of odd degree. If it is there, then definitely it has an Euler path. For the Euler circuit, degree of each vertex is even. Now K4 does not possess Euler circuit because it consists of odd degree vertices. What about the path? But we are getting more than 2 vertices of odd degree. It means it does not has Euler path. What about the K5? So degree of each vertex is even. So it means it has an Euler circuit. But not an Euler path because we are not getting exactly 2 vertices of odd degree. What about the K3? Degree of this vertex is 2, degree of this vertex is 2, degree of this vertex is 2. So it possesses Euler circuit, not a Euler path. What about this one? 1, 1. It possesses Euler path rather than a Euler circuit. Exactly 2 vertices are there of the odd degree. Now for the K1, so degree of this vertex is 0. There does not exist any edge in this graph. So it means we cannot comment for the Euler path and Euler circuit. Now we can generalize this. So K3, K5 has Euler circuit. But only K2 has Euler path. So you can check it for every odd number of vertices. It has an Euler circuit. But only for the K2 there exists an Euler path. So in a complete graph, total number of vertices are n. Edges are n into n minus 1 by 2. So it has an Euler path. Yes, only in a one case, that is for the K2. Euler circuit, that is for the n where n is odd. and n is greater than equal to 3. Next, we need to check whether it has a Hamilton path or a Hamilton circuit. So means we need to cover each and every vertex. Can you do that? So let's try it. So for the K2, can you cover each and every vertex exactly once? So answer is yes. You can start from here. You can directly move to this one. So endpoints are different, means it has an Euler path. Does it has an Euler circuit? So when you come back, in this case, you are repeating the edge. Since we need a simple path, no repetition of the edges. So K2 has only Hamilton path but no Hamilton circuit. Now what about this one, K3? So start from this vertex, then move to this third, and we can also come back to the first one. It means it has both Hamilton path as well as Hamilton circuit. Now in this case, did you get any circuit whose endpoints are same? So yes, you can start from here, move to the second, then third, fourth and fifth. So it has a Hamilton circuit. So definitely it will have a Hamilton path by removing the last vertex. What about the K5? So starting from the 1, 2, 3, 4, 5 and we can also come back to this one. So in this case we are not repeating any edge as well as a no vertex. So it means it has a Hamilton circuit. So if a graph has a Hamilton circuit, definitely it has a Hamilton path. So we can say that a complete graph in a Hamilton circuit for Kn where n is greater than equal to 3, but it has a Hamilton path for Kn n greater than equal to 2. Now let's move to the next one, Cn. So Cn consists of n vertices. Now we need to identify the number of edges in this case. So C3 indicates that total number of vertices is equal to 3. So make sure for the cycle the count of number of vertices starts from the 3. There does not exist any cycle of 2 vertices. So in this case, so total number of vertices are 3 and in this case 4, 5, 6. So the subscript represents the number of vertices. Now total number of edges in a C3, 3, C4, 4 and in a C5, 5, C6, 6. So total number of vertices in a Cn is equal to n and number of edges in this case is equal to n. Now we need to identify whether it has an Euler path or Euler circuit. Calculate the degree of each vertex. Once you calculate the degree of each vertex, you can observe that the degree of each vertex is 2. So basically Cn is 2 regular graph. Since the degree of each vertex is even, so we can say that it has an Euler circuit but not an Euler path, because for the Euler path we need exactly 2 vertices of odd degree. Now does it possesses any Hamilton circuit? So answer is yes. It's very easy to identify in this case. You can start from any vertex. Suppose you are starting from this one, move to this, then third, fourth, fifth and come back to the first one. So it has an Hamilton circuit. Similarly for C6, start from the first, second, third, fourth, fifth, sixth and back to the first one. So if it has an Hamilton circuit, then definitely it has an Hamilton path. So Cn has Hamilton circuit, Hamilton path, Euler circuit but no Euler path. So next simple graph is a wheel that is represented by Wn. Now W3 is formed with the help of a cycle C3 and we are taking the additional vertex that is connected with the rest of the vertices of C3. Similarly for the W4, first we will take the cycle of length 4 and then we will take the additional vertex connected with the rest of vertices of the cycle. And same for the W5 and W6. So in W3, total number of vertices are 4. In W4, 5. In W5, there are 6 vertices. In W6, there are 7 vertices. So if you say that Wn, then the number of vertices in this case is n plus 1, where n indicates the number of vertices from the cycle and 1 is the additional vertex. This is also called as a universal vertex. For the total number of edges, first we will calculate the degree of each vertex. So here I have mentioned the degree of each vertex. So you can observe that in W6 there are 6 vertices of degree 3. So in this case, if you add this one, this is as equal to 6 into 3 plus. So degree of the central vertex is 6. Now what is the degree in the W5? So if you observe that there are 5 vertices of the degree 3, this can be written as 5 into 3 plus the central vertex degree is 5. So this is the total degree for the W5 and this is the total degree for the W6. Same you can write for the W4, that is 4 into 3 plus the degree of the universal vertex is 4. So now you can generalize this one. So in Wn, n vertices are there with a degree 3 plus the universal vertex degree is n. So the total degree in this case is equal to 4n. Now we need to count the number of edges, that is equal to the total degree divided by 2. So in this case total number of edges are 2n. Now for the Euler circuit, degree of each vertex must be uneven. So clearly you can see that the degree of the outer vertices are 3. It means in any of the Wn there does not have Euler circuit. What about the Euler path? For the Euler path, exactly 2 vertices should be there of the odd degree. So clearly it indicates that there does not exist any Euler path as well as a Euler circuit. What about the Hamilton path? So can you cover each and every vertex exactly one and you can come back to the same position? So let's try it. Start from the W3. You can go with this one. Start from the first vertex, move to the second, then the third, then the central vertex. From the central vertex, we can move to the first one. So there exists a circuit of length 4. So yes, it has a Hamilton circuit. What about the W4? So let's try this. So 1 to second, second to third, third to fourth, fourth to the central and central to the first. So there exists a circuit in this case also. What about the W5? First, second, third, fourth, fifth, move to the universal and go to the first one. So yes, there is a Hamilton circuit in this case. So we know that if a graph has an Hamilton circuit, definitely it has a Hamilton path. Next we are moving to the complete bipartite graph. So here we have considered the few cases of a complete bipartite graph. First is a K2, 3, that is also is equal to K3, 2. So in this case, total number of vertices are 5, that is the sum of these two. Even in this case, total number of vertices is equal to the 2 plus 2, that is equal to 4. So in KMN, number of vertices is equal to M plus N. Now number of edges in this case. So there are 2 vertices of degree 3 and there are 3 vertices of degree 2. So the total degree is equal to, in this case, is 2 into 3 plus 3 into 2. That is also written as 2 times of 2 into 3. Consider the case of K3, 4. So there are 3 vertices whose degree is 4 and there are 4 vertices of the degree 3. So the total degree in this case is 4 into 3 plus 3 into 4. So that is twice of 3 into 4. So the total degree in this case is twice of m into n, but we need to count the number of edges, so divide by 2. So the total number of edges in this case is m into n. Now let's try to explore whether these graphs has an Euler path or Euler circuit. So in a K3, 4, in this case there are more than 2 vertices whose degree is odd. It means it has no Euler path. In this case neither the Euler path nor the Euler circuit exist. So in a K2, 3, so 2 vertices are there of a odd degree. It means it has an Euler path but no Euler circuit in this case. So in this case we have Euler path. What about K22? So degree of each vertex is even in this case. It means it has an Euler circuit but no Euler path. K33. So there exist more than two vertices of odd degree. So it clearly indicates that neither Euler path nor Euler circuit exist in this case. Now you can generalize this one. If K, M, comma N is there, so it has an Euler circuit if and only if M and N are even. Whereas a complete bipartite graph with the two vertices of odd degree means there must be two vertices of odd degree. If I write this as N, so it has an Euler path if and only if N is odd. Now for the Hamilton circuit, a complete bipartite graph has a Hamilton circuit if and only if the number of vertices in a first set is equal to the number of vertices in a second set. So you can check it in case of K2, 3, you will not get a Hamilton circuit. So let's try in a K2, 3 graph. So if you start from the bottom vertex, so you can move to this vertex, then middle, move to the upper vertex, then the third vertex. Now we cannot come back to the starting vertex because there is a no edge from this vertex to this one. So it means it has no Hamilton circuit. Now what about the Hamilton path? Did you get any path that cover each and every vertex exactly once? So answer is a yes. You are getting a zigzag form over here. So even in the K3, 4, so you will get a zigzag. So start from this vertex, move to the bottom vertex, then the upper vertex, bottom vertex, upper vertex, bottom vertex, and the upper vertex. So in this case, you will get the zigzag form. So by this, we can cover each and every vertex. So we can say that every complete bipartite graph has a Hamilton path, but it has a Hamilton circuit only in a one case when the number of vertices in a one set is equal to the number of vertices in a second set. So we have total number of vertices in a complete graph as m plus n. Number of edges is m into n. And the complete bipartite graph has an Euler path for only in this case when we are dealing with the complete bipartite graph with the two vertices in a one set and n vertices in another set where n is odd, and it has an Hamilton circuit when m and n both are even. It has an Hamilton path in each and every case. But for the Hamilton circuit, the number of vertices in a first set should be equal to the number of vertices in a second set. Simple graph is a cube that is represented by Qn, and in this case we know that total number of vertices are 2 raised to power n. Now let's calculate what is the number of edges in this case. We know that the Qn is a hyperbolic cube in which there is a vertices representation, that is a bit string of a length n. Suppose we are dealing with the Q1, so there are two vertices and they are represented by the bit string of length 1. Now in this case, the degree of this vertex is 1. Degree of this vertex is 1. So it's a one regular graph. So Q2, degree of this vertex is 2. 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 So degree of each vertex is 2. It is a 2 regular graph. Now for the Q3, degree of each vertex is 3, and therefore Q3 is a 3 regular graph. So you can remember that in a Qn, n represent the degree of each vertex. So basically it is a n regular graph. So total number of vertices in this case is 2 raised to power n. So for the number of edges, we will say that 2 raised to power n into the degree of each vertex divided by 2. That is equal to 2 raised to power n minus 1 into n. Now we need to identify whether it has an Euler path or Euler circuit. So for the Euler path, exactly two vertices are there with the odd degree. It means it has an Euler path, but no Euler circuit. What about the Q2? So degree of each vertex is even. It means it has an Euler circuit, but no Euler path in this case. What about this? Degree of each vertex is 3. It means it has no Euler path and no Euler circuit. So we can say that in a Qn, if n is even, then it has an Euler circuit. And only for the case of Q1, we have Euler path. Now what about the Hamilton circuit and Hamilton path? So in this case, can you cover each and every vertex exactly one without repetition of a vertices and edges? So in this case, we can cover each and every vertex exactly one, but the endpoints are not changed. So it has Hamilton path, but no Hamilton circuit. So what about Q2? Can you cover each and every vertex exactly once? So yes, even we can reach back to the original position. Therefore, it has Hamilton circuit. So if it has a Hamilton circuit, definitely it has Hamilton path. To easily understand whether it has a Hamilton circuit, I have renamed these vertices. Now let's try to find the Hamilton circuit in this case. So start from the vertex 1, 1 to 2, 2 to 3, 3 to 4, then move to the 5, then 6, 7, 8, and from 8 you can go back to the first. So you will get a Hamilton circuit in this case. So Q3 possesses Hamilton circuit as well as a Hamilton path. So in general, each and every Q1 has Hamilton circuit as well as a Hamilton path, except Q1, it has only a Hamilton path. So we found these condition for the Q. So total number of edges is 2 raised to power n minus 1 into n. Euler path exists only in a Q1. Euler circuit for every Qn when n is even, and Hamilton path exists for every Qn. But for the Hamilton circuit, we need to start from the 2.